Okay, so let's start again now with Jean-Christophe Tremblay de l'Université de Rennes. And he's going to speak about stochastic dissipative quantum dynamics. Very good.
Thanks. Well, first, thank the organizer for giving me the opportunity to talk at this meeting. Do you hear me correctly? It's online, so it's not clear for me if you can hear me properly. Just yell if you, I'm going to get along with that. And if you don't understand, just don't hesitate to interrupt me. So I'm going to talk about our recent work on stochastic dissipative quantum dynamics. This is work that has been done in collaboration with Fabien Gatti and Roberto Marquardt. So two colleagues you know very well. And mostly the work of Tobias Sarvatka, who started with these scattering experiments that we tried to simulate using these type of methods, and Suvik Mandal, who implemented the stochastic MCTDH method, as we'll see later in this talk. So the main goal, so I'm going to talk about stochastic dissipative quantum dynamics. So the main goal is really to study the quantum dynamics of a small system that would be in contact with a large environment. Right? And this is depicted here as a cartoon to say that we would like to shine some light or to bring our system out of equilibrium. So the system is represented as a collection of orange beads. And this system is in contact with a bath. And this bath will then take some energy or exchange energy with the system, such that the system will be driven towards thermodynamical equilibrium. The different mechanisms exist for this exchange of energy in phase between the system and the bath. These could be electron hole pair creation and annihilation. These could be electron phonon coupling, as you see in the middle in blue, or vibration phonon coupling, or internally non-adiabatic couplings as electron vibration coupling within the system of interest. You could also have some transient hot electron that would be attached to the system, and that would kind of transfer some energy and eventually go towards thermodynamical equilibrium. So the specific conditions that we're going to focus on today, so we're going to study an environment that is large and can thus be treated as a bath that would remain in thermal equilibrium at all times. So it's not going to be impressed at whatever is happening in the system, or at least we're going to treat this in mean fields such that kind of neglect completely what is happening in the bath. It is just a very large ensemble of degrees of freedom that are thermalized. And the other condition on this bath would be that the time during which the coherences in the bath survive are short compared to the system dynamics. So the time scale of the dynamics is really long compared to whatever time is that we have correlation inside of the bath. And under these assumptions, then we can derive a certain number of equations of motion, and we'll see how we can implement it in a stochastic way. More specifically, we're going to focus here on a typical surface scattering experiment, and later some kind of a fictitious surface system where we have a metallic surface that acts as a reservoir. So it's a very large number of degrees of freedom. And these degrees of freedom are electronic, and then you can create electron hole pairs that recombine, and they will lose coherence rapidly compared to the time scale of the system dynamics. So why are we interested in this type of system? Well, there are a lot of experiments that have been done over the years, especially in the group of Alec Watke, where they have actually shoot some diatomic molecules on these metallic surfaces. And then what we get is some kind of energy exchange. Sometimes electrons are transferred. We don't know really what is happening in there. Lots of theories has been done, like mostly classically. And then what we get is some kind of a product distribution that we can analyze. And for a specific example here, a highly excited vibrational NO scattered from a gold surface. So highly vibrational excited is a V initial is equal to V equals 15. So we have like 15 quanta of a vibrational excitation. It hits the surface and then it de-excites within a few hundreds of femtoseconds, by 7 to 8 quanta. So the product distribution is dominated by a loss of 8 quanta vibrational energy. And this happens on a very, very short time scale. And there were a lot of different studies after this one in Nature 20 years ago, Science, where they have actually looked at the effect of molecular orientation, of non-adiabatic coupling and coupling to the phonons, and the question that we are going to be interested in today is the effect of vibrational quantization, or at least in the first part of the talk. As I said, so this is a typical case where electron-hole pair is dominating, and we're going to come a little bit to that in a second, which means that this bath will be a large metallic environment where we have a large mismatch between the mass of the projectile, so the atomic molecule, and the metallic surface. So the large mass mismatch means that we have an electron-hole pair coupling that is of Markovian type. That is, it satisfies the conditions that we have imposed on our bath. And although the equations that I'm going to present today could be extended, and some of the concepts could be extended to non-Markovian situations, we're going to exclusively focus on this type of Markovian situation. So there's a large body of work on that, and how do we treat that? So typically people would treat this type of system classically, so they would have a potential energy landscape on which a dynamic would occur. They would shoot a few hundreds of thousands of classical trajectory distributed according to some principles, or quasi-classical type of distribution. And then these particles, these diatomic molecules, would obey some equations of motion that are classical, where we see the potential occurring, and some two terms in the generalized Langevin equation. One would be the friction that is opposed to the motion of the nuclei. So the nuclei are moving, and they're going to be thwarted by the effect of the environment. And then it would just go to 0 Kelvin. And at the last term, we see a random force. The random force is there to impose the fluctuation dissipation theorem in the ensemble of those different trajectories. So there's a connection between this classical view of things and quantum mechanical view of things, where I would say that if we have relaxation, then we should definitely have some kind of a jump between a higher lying vibrational state that is quantized to a lower lying vibrational state. And this connection goes via the friction tensor and the phonon self-energy. So imagine that we can calculate the phonon self-energy for a system. It is connected by the fluctuation dissipation theorem to the friction tensor, where we see the stochastic forces applied on the atoms. They act, and they can be taken as the real part of this object. And these stochastic fluctuations kind of induce this friction that is opposed to the motion of the projectile. If we look on the right side, we see the relaxation rate. They are also some kind of a local harmonic approximation is hidden in there, but the connection is as taking the imaginary part of this self-energy, and this gives you the relaxation rate that is a quantized relaxation from a higher vibrational state to a lower vibrational state. So this connection is there, but no, in the dynamics is never kind of really made, in the sense that we do classical dynamics, and we wanted to kind of investigate the effect of vibrational quantization on the relaxation process, which should take a form that is a bit different. So the approach is to look at the total wave function and to look at the quantized state. That is, we have vibrational state that are here represented as psi of q, and we have electronic states that are represented as chi electron r and q. So on the left-hand side, we see that we have a continuum, basically. It's because we're on a metal. Each of these electronic states is essentially part of a band of many electronic states. So imagine the situation where we start with an electronic state that is lowest in energy, the red one, on which we have a nuclear density that is represented as the red thin line. Since we have a continuum of state, what we'll observe is that at the same energy, we also have a vibrational state in blue on the right, in the central panel, let's say, that is contains less nodal structure and hence less energy, but contains more electronic energy. So we would refer to this blue potential energy curve that is parallel to the red energy curve, the bottom one, as an excited electron hole pair of some sort. And these electron hole pairs, they will recombine rapidly within the metal and lose any memory of the interaction with the substrate. So what has happened from the perspective of the substrate or the projectile or the system at hand is that we have lost a few vibrational quanta, and the blue potential energy curves rapidly decays to the red curve. So this is phenomenologically what happens within the system and bath. And now the right-hand side shows you the little picturesque way of looking at vibrational, a quantized vibrational relaxation, where we see that from the perspective of the system alone. It's as if we were in the global ground state in red, and then we would have like jumps between different quantized vibrational states. The effect of the bath or the environment on the system vibration can be thus described by jump operators. These jump operators will take a wave function here in the state M and bring it into state N at the rate gamma Mn. And this can be represented relatively simply if we have the eigenstates of the system and the quantized eigenstate of the system as being a transfer from state M to state N. And the opposite is also possible, taking the vibrational state N and exciting it at the rate gamma Nm, and the relation between gamma Nm and gamma Mn, so the upward and downward rate, they would be related by detail balance, and then we can impose thermal detail balance on these two rates, such that the system will be driven towards thermal equilibrium. Another thing that we're not going to discuss so much today, but for completeness, it's the elastic collision that would occur. That is, we would create a virtual electron hole pair that will not recombine, but just add some wiggling to those states. And this will lead to so-called purity phasing. So this will be neglected throughout, but this is also something that comes out of perturbation theory. Well, speaking of perturbation theory, so we kind of developed expressions to be able to understand what is the rate that I was telling you about. So the transfer rate between some state I to some state J. I'll call them N, M, and N in the previous slide. So what we have is we have an initial state, and it's essentially kind of driven by non-adiabatic couplings. And what we see here is we have a strength of a non-adiabatic coupling that is proportional to N to the 1/3. That is, N is the embedding density, so the density of electron hole pairs surrounding the vibration. And we have a derivative with respect to the nuclear coordinate. And then we have a few proportionality constants that we can find from first principles. And this is kind of very elegant. So the basic physics is that we would imagine that we have a traveling electron from the metal transiently trapped on the bridge in green, and then going back into the sink. And then by doing the perturbation theory, by accounting for occupied and unoccupied electronic states, then we get this rate. We need to do some few approximation to get there, but I'll just not tell them so much. So I was telling you about the embedding density. The embedding density gives a position dependence to the non-adiabatic couplings that you see here. So we're not kind of frozen in a local perspective. We really have to kind of consider a large amplitude motion. And during this motion of the adsorbate or the projectile on the surface, then the density of electron hole pair will change. Because imagine the situation where you're very far from the surface, there's no interaction of the molecule or atom or projectile with the electrons of the surface. Once you get close to the surface, though, then there's a higher density of those electron hole pairs, and they will accelerate the rate at which we jump from one state to the other. And to the right, you see a few different embedding densities where the dots represent position of palladium atoms that were used in that study. And the rest are just contour lines telling you where the density is. And these are different models to represent this embedding density of electron hole. The beauty of this model is, as I mentioned earlier, there's a friction term that is connected to a local harmonic relaxation rate. And in this model, the way we do it, at least, it's possible to also have unharmonicity taken into account, provided we can calculate eigenstates of the system. And what we get is, we get transitions that would be otherwise not allowed in the harmonic system that might also accelerate the rate of relaxation of our system or thermalization of our system. So we would like to investigate a system bath dynamics using these rates that are essentially used to rescale the dynamics of our system in contact with the environment. So this is again depicted here. We have electronic states of the metal that can be excited and at the same energy. We have vibrations that can be de-excited, and through the nuclear kinetic energy, as a coupling through the nuclear kinetic energy operator, we exchange the energy between the two. The electron hole pairs we combine, we lose memory and we lose energy and we lose memory of this interaction. So these could be, as we're studying here, so the adsorbate vibrations or scattering, coupling to electron hole pair and metallic surface, but this could also be a light excitation of a chromophore in a very, very large protein environment where ultra-fast vibrational energy redistribution would essentially kill the coherences in the bath very, very rapidly. To represent this pictorially, what we have is we have a system in orange, that's just the line at the bottom, and in contact with the bath. Here, these are the electron hole pairs. And if we try to write the density matrix of the whole system bath, it could be represented here on the central panel as a collection of boxes for all possible states and coherences in the bath, and these are blue boxes, and within each blue boxes we have a replica of the system, and all of this is coherent. This is quite complicated, so we don't save a lot by representing our system bath in this way. But it allows also to trace the bath parts. That is, we're essentially flattening out all of these boxes together. So all the replicas of the system, they lead to this reduced density matrix that is represented on the right. So the row S represents only the system of interest, where the diagonal elements are typically interpreted as populations of the system in the basis that we have chosen for its representation, and the coherences in that basis. And the blue springs represent phase and energy loss. So these are the rescaling terms that we see in the dynamics that will affect the evolution of the system. So how do they affect the evolution of the system? Just imagine that we start with an initial coherent state. So the element row 10 is wrong, sorry about that. So we start with a fully coherent system, and then we let the system evolve in contact with the bath. So depending on the process of interest and depending on the strength of the coupling, we'll see these coherences disappear, and we're going to be left with only diagonal elements. So we're going to evolve from a coherent initial conditions towards an incoherent classical representation that should obey at least some thermodynamical properties. That is, we would like to evolve towards the thermodynamical equilibrium. Unfortunately, this is quite expensive numerically to solve that problem, and there is an equivalent yet maybe more elegant way of solving that problem. Instead of going directly at the density matrix or the reduced density matrix, we're going to look at the density matrix as an incoherent average over an ensemble of wave packets. This is more general than just the stochastic Schrödinger equation, but we're going to focus on that application right now. So we would like to kind of unravel this reduced density matrix as a collection of wave packets. We have NR wave packets, and each of these wave packets evolve independently from the others. So if we have enough wave packets, is it possible to recover an ensemble average that would give us exactly the density matrix evolution? And the answer is yes, right? And it can reproduce the equation of motion of the reduced density matrix up to some order, the one that you would choose. So each wave packet now would have to evolve according to some stochastic Schrödinger equation, where we have here two terms. We have the variation of the wave packet, of the wave packet of the system, or the state of the system, that will be affected by a term here, the Hamiltonian, that will contain some kind of a dissipative contribution and some fluctuation. And there's like a large body of work on that, and some people have different methods and so on and so forth. But what I really have here is a simple kind of general formulation for this stochastic Schrödinger equation, which upon averaging over many of them will reproduce the evolution of the reduced density matrix to some order. And depending on the master equation that you would like to reproduce, then you would get different set of Hamiltonians and fluctuations. Here we focus solely on the Monte Carlo wave packet method that is tailored to reproduce, or the way I know it at least, is tailored to reproduce exactly the Lindblad equation of motion which inserts semi-positivity of the diagonal elements of our reduced density matrix, and hence the probabilistic interpretation of the diagonal element of the density matrix as population of the basis functions used to represent the density matrix. All right, so from this reconstructed density matrix, we could calculate all sorts of expectation values, and then we would get the expectation value of the ensemble and not of a single realization of this stochastic process. So the realization of the stochastic process is quite difficult, and it's difficult to propagate the fluctuations themselves. And there is no reason to propagate those fluctuations because they're short-sighted, so they don't have any memory of the interaction. So that is, they actually are time local. They're just at this specific time step. So the alternative to propagating both the wave packet and its stochastic increment or its fluctuations is to look at the Monte Carlo algorithm, Monte Carlo wave packet algorithm, that propagates part of the system affected by the dissipative part and sample the fluctuations stochastically. So how does it work? So we have a deterministic part of the stochastic Schrödinger equation that is written here, where we have explicitly given the dissipative part, and this is a non-Hermitian operator that leads to a loss of norm, as you could recognize with the IH bar over 2 and sum over this these dissipation operators. These dissipation operators, in our case, in the first case we're going to study, are essentially jumps from one vibrational state to another vibrational state. Now, if we propagate this deterministically, we will have a loss of norm. So this is represented as a first time step here. So we have an exponential decay of the norm as affected by this dissipative part. And at some point we stop, and then we compare this loss of norm with some random number. And this first random number is the one that you see at the bottom, and it is smaller than the norm is. And hence we would say there is no jump inside of the at this particular time step, so there was no fluctuation. And to keep the probabilistic interpretation of the wave packet, we're going to renormalize it and propagate further. At the next time step, we decide to evaluate it, so let's say 1 femtosecond. We're going to compare this norm again to another random number, which is the highest blue random number you see on the slide. And then it's again lower, and hence we just renormalize the wave packet. And the system has evolved in time because of this dissipative term. And from this new initial condition, we just go further and further and further. And at some point, so the third time step, we see that the norm is suddenly smaller than this new random number that we pick. Right? So, and it's depicted in red. And this red tells us that we have a jump. And this jump means that we're going to have a collapse of the wave packet on one of the dissipative channels represented by these AK operators. So the operators that represent dissipation, they also act as collapse of the wave function for the fluctuations. And then we propagate further, and then we compare again at the fourth time step with a random number. The norm is larger. There is no jump until the next jump occurs, and then so on and so forth. These random numbers being independent, all the realizations will be different. And then if we average over all of this, then the wave packets will jump at different times. So we're going to have sampled the different fluctuations, the waiting time until the jump, using like randomly selected numbers. And then we're going to eventually have wave packets that evolve individually, they evolve coherently, but as an ensemble, they lose coherence among each other because they jump at different times. So the collapse itself in itself is interesting. So how do you do that? So once you have identified that you jump, you need to renormalize, you need to collapse your wave packet on some dissipative channel. And this is done using the cumulative reaction probability. Here for these Markovian rates, this is given simply as acting the dissipative channel on the wave function and making sure that this is normalized to 1. And then we're going to compare these different cumulative reaction probabilities with a new random number. And this will allow us to identify on which channel we have jumped. So by comparing this random number with the cumulative reaction probability. And having identified now this jumping channel, so the channel on which we're jumping, the wave packet is going to be collapsed as shown just above as the projection of the wave packet on this specific channel, and then renormalized. And this is our new initial condition for the further propagation of the system that will evolve under the application of this deterministic nonlinear operator. Right. So how does it fare? So we have started with this specific problem where we have a NO molecule that is vibrationally excited that we're going to scatter on the surface. And what we see is as we get closer to the surface, this is depicted on the right-hand side, the internal degrees of freedom have some kind of a vibrational relaxation rate that can be calculated. And there is an enhancement factor due to this embedding density I was telling you about, so this density of electron hole pairs. And as this projectile approaches the surface will then increase the density of those electron hole pair and increase the rate of the coupling. And this is depicted with three different pictures in blue, green, and let's say gray and black, where we have the relaxation close to the surface and the relaxation as the projectile approaches the surface. On the left-hand side, we're going to see two different of the time evolution of different expectation values. One of the population of the internal vibrational state, that is the stretch of the NO molecule as we're approaching the surface. We're starting the V = 3 state, the vibrational state of the molecule, and we shoot this at the surface. The probability density in Z is depicted at the bottom to help us see what happens, where's the center of mass and how much it spreads as it hits the surface. So what we observe is then the wave packet at the bottom approaching the surface. And as we approach the surface, we're going to feel the topology of the surface, and which means that the vibrational state of the NO molecule will lose their character, will hybridize a little bit. So we have a stretch here. And this means that we're going to mix the V = 3 with the V = 4 and V = 2 vibrations. And now we have seen a first jump. So what has happened is we have collapsed our wave packet into some Z state and some V state. And there is a second jump occurring and a third jump will occur again. So you see the wave packet starts to move away from the surface, and now it's going to collapse again close to the surface. So it's very hard to predict what will be these jumps, but in a single realization of the stochastic process, we see a lot of the physics that is of interest to us. And then part of the wave packet sticks to the surface and part of the wave packet leaves. And then we freeze essentially the population, the vibrational population of our system, as you can see up there. So the red state, that was the V = 3, is now about 60% population, 50%. And the V = 2, V = 4 now becomes populated. Not so much because there is an excitation, but rather that we kind of freeze this stochastic realization on a specific moment when at the surface. And at that moment, we have a strongly hybridized V = 3, V = 2, V = 4 state, and then hence this is the wave packet that comes out. So if we look at the evolution of this wave packet in a static fashion, so we have the motion at the center of mass, it hits the surface, and there will be 3 jumps. These 3 jumps are represented to the right. And we see that the wave packet before and after the collapse of the wave packet, so this side is decided stochastically, so there's really no way to know at one time step where we're going to be at the next one if there's a jump. It's really kind of randomly selected from the relaxation channel available. Okay. Now, if we average over many of them, so a bit more dirt is given here with the initial conditions, but it's what I would like you to focus on is that the average evolution of the system, where you see that the deterministic wave packet hitting the surface would go away more rapidly than one with electron hole pair coupling. So averaging over this allows us to recover the evolution of what we call the stochastic density matrix. We see that it's kind of slowing down the process, and there's always some probability density that remains sticking to the surface in a long time. So these are things that we would expect, whereas the deterministic wave packet just spreads a little and goes away. Now, this has a very large effect on orientation, as we can see. So for different sites on which we collapse the wave packet, or we collide the wave packet with the surface. We see different distributions, and the top and bottom panel in each of the two figures on the left give us the quantum dynamic simulation, where we see it's very broad spread of the different rotational J states in the outgoing channel, while in the molecular dynamics with electronic friction, so the one with the Langevin dynamics or classical distribution, we don't see this rotational rainbow for the top side at least. And this can be pinned down mostly to kind of orientational effects. And we see on the right here the average orientation of the molecule over many realizations. So different number of realizations are given. So this is why you see three curves in blue, green, and purple. And if you look at single stochastic process, you see that when there's a jump within, so when the wave packet collapses because the fluctuations are affecting the dynamics of the system, then we see there's a large collapse and there's a large mixing of those J states because we have a strong orientational effect. And this is a combination of the topology of the potential and of the relaxation that freezes the system in some kind of a J state. But you see that it's kind of a mixture, even for a single wave packet, and then it goes away. And then we're going to have an average over that. And this is why we see a strong orientational effect that needs to be watched over many rotational J state in the outgoing channel. Now, this is all nice and well, but we would like to study this type of system here using, well, in higher dimensions, so towards high dimensional quantum dynamics. So Fabien, Roberto, and Suvik, and Usama and myself have been working in this direction for the last 2 years. So the idea would be to improve upon the propagation of the wave packet that we have and go beyond the eigenstate basis, but while retaining the advantages of the Monte Carlo wave packet. So the first thing to do is to go with the best propagator available for large high dimensional quantum dynamics is the multi-configuration time-dependent Archery method, where in a nutshell, what we have is a redundancy in time dependence, where we have coefficients that are time dependent that multiply products of single particle functions that also evolve in time. So these are coupled equations of motion. I'm not going to go through this. This has been very well implemented and pushed forward by a lot of our community. So, and it's a well-maintained program package. So the one in Heidelberg, at least, is and also Quantix. So these are very well-maintained packages that we could use, but they miss one thing. They miss essentially this this non-Hermitian term that we're talking about, that leads to this dissipation that will help us to define dissipative channels. Now, if we would like to stay in the eigenstate basis, then we need to diagonalize the whole Hamiltonian, defying the purpose of a generic high-dimensional propagator. And so we would like to retain some kind of a sum of product form to represent the relaxation rates that would kind of convey the same meaning as what we had before, that is the relaxation between quantized vibrational states. So the way we did this, so we kind of did some reverse engineering of some idea that Shifu Gao published 20 years ago in 1D to extend this to multi-dimension and to see, so how does it fare for many as a high dimensional system? So the structure of the dissipative operator that we have takes the following structure. So what we have is we have a sum over the different degrees of freedom. We have k equals 1 to f, and for each of them, we're going to have a M operator that will try to satisfy detailed balance the best they can. So some reverse engineering of these coefficients allows us to kind of propose this following a definition for the constants that we have here are a combination of position, momentum, and relaxation operator. We recognize AK3 for a given degree of freedom as being a generalized lowering operator. And then we get W, which is a function of the coordinate, and P, that is the associated momentum with this coordinate. And so we interpret the kappa as being some kind of a relaxation rate. So we have a dissipative part to this whole set of operators for a given degree of freedom, and we have a fluctuation part. We interpret this as a fluctuation part where we have a mu k of t and a nu k of t that can be given some specific form. And in the low temperature regime, so we find these three definitions that are given down there. And We see that there is a temperature dependence explicitly in both the mu and the nu, but there's no temperature dependence in the kappa k, so for a given degree of freedom. So the connection between these allows us to retain the product form for the MCTDH, and hence we sort of do nice work by Subik Mandal, who did all of this implementation, the simulation for this work. It's essentially we try to retain, to be minimally invasive, and then we just put a few words or modifications in the MCTDH code such that we output something and some informations, and then decide if there's a jump, and then the MCTDH program is stopped. So we haven't changed the MCTDH, we retain its efficiency, and then we calculate the cumulative reaction probability, identify the channel on which we collapse, define the new initial condition, and restart the MCTDH run. And this until we have reached the end of the propagation. And then we just concatenate all of these information, all of these jumps, and compute all the expectation values and average that we would like to have. Nicely, we can run this once, twice, 20 times. If we know the system and the propagation time we would like to propagate, we could just run one trajectory after the other, and then we just increase the quality of the average values that we get. So in red, you have here those input and output files that we get that we need to kind of feed this SMCTDH algorithm. So this is a minimally invasive modification to MCTDH. It's not extremely efficient because we don't want to tamper with the program, but at least for slow, relaxing processes, then we can do a lot of stuff with it. And we wanted to study, as good physicists, we would like to control pretty much what is happening. So we don't want to kind of just study a specific system. We would like to understand what is the effect of intermode coupling and how is it intertwined with relaxation and thermalization of the system. We take an example here, a two-dimensional model where we have a harmonic coordinate and a Morse coordinate representing the internal degree of freedom of an O2 molecule scattering from a platinum surface. So the distance of the center of mass of this O2 to the surface is then given as a Morse coordinate. And we have the potential, model potential that we use here on the left, where you have like quadratic potentials on these two coordinates plus a bilinear coupling term that we can control with the coefficient C. Now, depending on the coefficient C, I'm just going to flash this slide here to so that we can calculate this. The 2D problems are relatively simple, so we can always compare with the eigenstates. So what are the populations of these eigenstates? What are the populations of the zeroth order states, that is, the modes themselves? And what are the energies of the coupled and uncoupled system? And what we identify here is that we have two vibrational states, one at about 400 wave numbers and the other at 870 wave numbers. They represent the two modes, the high energy mode and the low energy mode. So the internal stretch is at high energy. And what we observe is at state 10 and 11, they mix together. So that we have like the occurrence of some Fermi resonance, and there is some kind of a splitting that is about 24 wave numbers that will appear later in the talk again. So it's a mixture of highly vibrational excited Z mode and a combination mode of Z and R, a combination band of Z and R. Right, so the first thing we did was to test if the system was converging, or the implementation was converging well with temperature. So what we see on the left-hand side is the convergence behavior of the energy decay as a function of the number of stochastic realizations of the process. And then we see that it increases, the requirement increases like mildly with temperature. So up to moderate temperature of 400 Kelvin, we can get away with about 1,000 realization of the stochastic process to get decent statistics. And then we wanted to see, with different initial conditions, do we reach also always the same equilibrium? And still don't know what is the nature of this equilibrium. And what we see is, if we start with the ground state, this is the one in C and D at 200 and 400 Kelvin, we do reach some kind of an equilibrium. That is, the bath is heating the system. The bath is giving sort of electron hole pairs of the metal are heating the degrees of freedom of the O2 molecule. And that is what we observe. And then we reach some kind of a an equilibrium. In the top side, what we start with is a displaced harmonic oscillator, and then we see that it evolves. It contains many states along the Z mode and a few mixture along the R mode. And what we observe is that there is kind of an equilibration that occurs at even a bit longer time because the dynamics is further away from equilibrium. And if we compare these populations at longer time, the equilibrium is found to be the same in both cases. So independently on the initial condition. What we also observe is that this equilibrium condition, so it's still fluctuating a little, but we can look at the different populations of the different states, and we see that this equilibrium that we have observed is pretty much thermal as we extract from the inversion of the Boltzmann distribution. We report the ln Pn over P0 to the right, and they're given as stars with some bars that should not be interpreted as error bars, but rather as the width of the fluctuations that we have in the system. And we see that fits pretty well to the thermal behavior that we would expect from the Boltzmann distribution. So yes, we have an equilibrium, and this equilibrium is about thermal for weak coupling and relatively slow relaxation process. In view of the time going, so I'm going to skip that one and rather move to another aspect here of the relaxation behavior. So these stochastic processes, they lose their coherence, right? So what will happen is if we have a slow relaxation, we would expect actually coherences to survive for a long time. And typically in quantum dynamics, we say the coherences drive the dynamics and so on and so forth. But if we look at the weak coupling regime, so for C equals to 0.1 on the left-hand side, we see that the shape of those relaxation of these populations, they wiggle a little bit, but they do follow pretty much the one where we have like no coupling at all. So the coherences between the modes, they don't seem to play a very large role, and the dynamics seem to be completely dominated by these relaxation processes, at least in the slow relaxation regime. Now we can identify a few relaxation channels, but I think this is just to show that if we have a fast channel, this is the R channel in this case, the relaxation is completely dominated by one of those relaxation operators. So we collapse mostly the wave packet along the R modes, we reduce the nodal structure at each jump, and then we heat up the Z mode via the ground state. So the bath is taking the energy and giving it back to the ground state to excite the Z mode. Ultimately, we have no population in the R mode and only population in the Z channel or Z mode that has actually the lowest energy of the two. One interesting fact, so I was talking about this Fermi resonance earlier, is if we kind of play a little bit with the lifetimes that we have here. So gamma Z is telling us what is the relation to, is it faster or slower than the relaxation rate along R, which is 2 picoseconds. On the left-hand side, we see that the relaxation is completely dominated by the Z channel, and all of these wiggling that due to the coherences are kind of washed out, and we see a very smooth dynamics going to the ground state and equilibrating to this thermal ensemble. On the left-hand side, though, we have a slow R channel and an even slower Z channel, which means that the Fermi resonance survives a bit longer. And this is here depicted in the green and orange line, if I'm not mistaken, or pink line, that have some beating that occurs here. And in the two different cases, of course, the fast channel will dominate relaxation, and in all cases, the lower state will be populated indirectly via the bath, as we've seen earlier. So what is this beating that we observe here? This is really the beating that we have observed in the Fermi resonance. So it's populated at the beginning, and all of these relaxation channels, they kind of follow pairwise and in a very strongly coupled manner down to the ground state. And this is why we see for the Fourier transform of this population, we see doublets occurring that correspond to pairs of the excitations or pairs of a relaxation that remains coherent up till we reach the bottom of the well, or bottom of the ground state of the system. Finally, what we see also is that we have an increase, a washout, or the doublet becomes completely washed away if we reduce the lifetime of the Z mode. That is, we increase the rate of relaxation along the Z mode. That is strong or fast relaxation due to the strong coupling to the bath, or stronger coupling to the bath will lead to kind of a loss of all of these nice features that we observe. And we see this in the purple line at the top end. For strong intermode coupling, as we see C equals to 0.5, this is the picture on the left, at the bottom left. We see that we can't really recognize the structure of this Fermi resonance because it does not appear in the eigenstate spectrum. Maybe the last thing that I would like to talk about is really kind of the problem associated with strong coupling. So we have shown that for a weak coupling regime, we managed to get thermalized equilibrium at the end of the propagation. So we have a very nice onset of the thermodynamical properties in the system, and this behaves very nicely. For strong coupling, we see that, so C equals 0.5 on the right, we see that we have like much stronger oscillations that decay also on a relatively short time scale. But we have a population that towards equilibrium reach the same for the R and for the Z mode. And this is impossible thermodynamically because both have different temperatures. And so these are eigenstates of the system, so they should actually kind of be distributed according to Boltzmann population. So we see the onset of a hyperthermal behavior in the high energy mode for strong coupling. So we wanted to explain what is the origin, the physical origin of that. So we first kind of check the reduced population and derive temperatures from that. So we just take the full density matrix and we trace out one of the degree of freedom to get populations of the different states. And from these populations of the different states of the Z mode or the R mode, we can determine temperatures. And what we see is that in both C equals 0.1 and 0.5 cases, so weak and strong coupling regime, we have a hyperthermal behavior or a hyperthermal R mode. So the question is, where does it come from? And our hypothesis was that it comes from intermode coupling. And we made a very, very simple model. That is, we have like thrown away everything that is not part of it and tried to understand analytically the solution to that problem. And what we've observed is, of course, the model is oversimplified, but the only thing that is left in this model is exchange of energy between the modes. And that is, we exchange with this potential coupling VZR, the energy between the states 1, 0 and 0, 1, and the state 2, 0 and 1, 1, which corresponds to creation, simultaneous creation, annihilation of the quantum in both cases, in both modes. And what we get is you know, so from MCTDH, we can calculate these matrix elements, we use them, and then we find that the population at the asymptote would effectively, in the low coupling regime, obey pretty much the Boltzmann distribution. It's written in red here, or dark red. And in the strong coupling regime, we see an inversion of this population, or at least it's even worse, actually, in our case. Now we see that we have an increase of the population of the R mode, so the high frequency mode, because of this intermode coupling. And we have found a way of getting rid of that in recent work, but I'm going to stop here. So by showing that we have done some Monte Carlo wave packet simulations. So we have implemented this in MCTDH to go further and to get away from, we have to write a single code every time we would like to study a new system. And to get away from the requirement of using eigenstate basis for the relaxation operators. So we have designed this sum of product, one-dimensional operators structure for the relaxation rate. So that is the coupling with an environment, that would be Markovian. Some numerical results show us that in strong intermode coupling regime, hyperthermalization is observed, but we have found a way to get around that. Yeah, so these are kind of the developments that we've been doing over the last few years. So these have been implemented, the last part by Suvik Mandal. And again, I would like to thank Usama, Roberto, and Fabia for the nice work together. And Tobias Sarvatka was the one involved in the NO gold scattering that you've seen. I would like to acknowledge funding and thank you for your attention.
Thank you, Jean-Christophe. Any question? Maybe, yeah, Roberto?
No, I was just thanking Jean-Christophe.
Sorry. I thought you raised your hand. Someone in the audience? I've got a question. I mean, when you're doing the MCPDH, so I guess you have some kind of several electronic state.
Yes, we also have a single electronic state. So we remain in the ground state. So this is really kind of a ground state theory where you start from the beginning. Here, we would kind of really always remain in the ground state, and we treat the electronic excitation as a perturbation that will take the energy or bring energy in the system. So we always have a single potential energy surface, but there is nothing telling us that we couldn't have two different characters, non-adiabatically coupled, so a strong coupling regime for, like, I don't know, ion resonance on the surface and so on and so forth.
And so if you use more than one electronic states,
yeah,
does it matter that you will have to work in diabatic states instead of adiabatic representation?
No, well, this will enter definitely the definition of those relaxation rates we've seen, right? So instead of jumping, so we're going to get there. Oh, too many animations. So these relaxation rate AK that I'm showing you. So these defined processes. And then we can always say that these processes, yeah, okay. So these processes are here, relaxation operators, and then we would have to kind of do a tensor product with the electronic basis. That is, do you allow only this electronic friction to occur within a single state, or do you also allow one state to be converted to the other? And I would say that it's probably better to have this strong coupling as a diabatic scheme, where you have like an ion resonance and a ground state that is neutral, and they're both coupled via some potential. So there will be some mixing. So this would be the strong coupling regime, where you have a strong change in the character of your electronic wave function. And then you would have internally these relaxations using these operators. That wouldn't change anything. We just need to kind of multiply by an identity matrix on the electronic manifold.
Okay, thanks. Other questions?
David, I perhaps would have a question to
trigger
a little bit the discussion, Jean-Christophe, that we are targeting here in this thematic week.
Yes.
And this is the question of quantum computing. My question is then really more general. To what extent is the approach that we have now been developing with the stochastic MCTDH, the wave packet method, so stochastic MCTDH, to what extent can it give us perhaps a more reliable information on how incoherences may affect or coupling to the environment may affect the working of a quantum computer? Compared to, let's say, what people have been doing in the past with non-Hermitian Hamiltonians?
Yeah, it is actually propagation under a non-Hermitian Hamiltonian, right? So this is really pretty much the same thing, but we have a proof that with this MCTDH or this stochastic Schrödinger equation, we can recover a Lindblad form. So that is, we have exact Lindblad propagation. So if we have a true system that we would like to treat for quantum computing, so that is, we have a molecule, we would like to address it, and we would like to see what is the effect of decoherence, we would like to see what is the effect of energy loss because of a contact with the environment, and these operators are well suited. If we would like to just look at decoherence, then we need another set of operators, but it's easier. These are just fluctuations. They're not collapsing so much the wave packet, but they would take a slightly different shape. Consider a projector on eigenstates. So it would look a bit different, but then we could use such operators to perform a simulation where we know that the ensemble of many realization of the stochastic process would reproduce the true reduced density matrix according to a Lindblad equation. That is, if you trust that the Lindblad equation is the right one. For quantum computing, that would be one thing. Mm-hmm. That would be the regime where we decouple the timescales again, right? So where we say that the bath is Markovian, is large, doesn't have the memory of the interaction with the system.
Thank you. Yes.
Let me just add as well, so if we want to go further and use some machine learning in that context, the idea would be to learn what modify the master equation. So not using the Lindblad equation, but changing the master equation to something that has a memory kernel, where the memory kernel tells you what is the effect of the system on the bath. So the bath has a memory of the interaction with the system, and this will be fed back into the equation. And if we could learn that thing, and then we would have a very, very nice non-Markovian model that can be mapped at some numerical cost, but can be mapped into a similar type of operators. We would have to be clever with the operators, though. I don't say that we have them, but if we have a non-Markovian machine learned type of equation with a machine learned memory kernel, then we could probably map this into some kind of a stochastic MCTDH propagation.
Other question or comments? Okay, so let's thank again Jean-Christophe and the other speaker of the afternoon.
So, David, are we now having a roundtable discussion? Is that the idea?
Yeah, why not? I know I'll have a discussion. Just a bit complicated. Share the microphone, but I'll try to do something. No, doesn't work. No. Okay.
I can hear only David.
Yeah, that's the problem. So when I speak here, do you hear me?
I hear you well now, David. Yeah.
Okay. And on this one, do you hear me? Okay, so anyway, we can switch to French. Non, je pense qu'on peut parler en français parce que je pense qu'il y a tout le monde est.
Désolé, je viens de voir ton message. I don't mind turning on my camera, but c'est un peu tard. Hein?
Je vais juste arrêter l'enregistrement.